Hi, EP1 students. This is your lecturer for EP1, Professor Samushia. And this is our first virtual EP1 lecture. I hope that all of you are doing well. I hope that this coronavirus lockdown will be over soon. Meanwhile, what we will be doing is I will be recording these lectures. I will also be uploading my lecture slides on Canvas. So as you listen to these lectures, recorded lectures, you should also be going through, you should have a second window with my slides open, and you should be going through those slides. Okay, let's see how this goes. So first of all, since we had a almost two-week break, I want to start by reminding you what we learned so far in EP1. This is a second slide on my slides. So we started from studying a motion. If you have a particle, an object, this object moves around. And we learned that this motion can be described in terms of velocity, in terms of acceleration. So if you have a position that you can describe by x, y, z coordinates, and if this position changes it in time, so for example, you may have a particle that moves from here to here along this trajectory, then you will have velocity. And if your velocity changes, then you will have acceleration. We also learned that the reason objects have acceleration is always because there is some other object that influences them. And we learned that force is equal to mass times acceleration. So if there is no external force that's acting on you, then you will have no acceleration. You will be moving with a constant velocity on a straight line. But if there is a force, then this force will cause some acceleration. We also looked at some simple forces. There was the force of gravity, mg. We had friction force, normal force, and force due to a spring and a rope, so-called tension force and the spring force. And we also learned that if you have two objects, so if I have object 1 here and object 2 here, if object 1 applies force F1, then object 2 applies an equal and opposite force F2. So the force of action is equal to the force of reaction. Now, if you know all the forces, then you can write down your Newton's laws, and you can find your velocity, your acceleration, your position. You can basically solve those equations, and you can see how this object is moving in time. But for some forces, we also learned that there are easier ways of figuring out how the force influences an object. So, for example, for the gravity and for springs, what we did was we were able to define this quantity called potential energy. For gravity, potential energy was mgh. For a spring, potential energy was k delta x squared divided by 2. And so we saw that for these forces, conservative forces, this thing called energy is always conserved. So there are many types of energy. You have potential energy of gravity, potential energy of spring. You also have kinetic energy. If this object is moving, it has kinetic energy, mv squared over 2. And so if you add them up, then, and if you don't have any other forces like friction, then your energy in the beginning is always equal to your energy towards the end. So the initial energy is equal to the final energy. And this is very useful because if you know that energy is conserved, then there are many problems that you can solve. And these solutions are very simple compared to if you have to, write down Newton's laws and go through all the mathematical machinery. Now, this is all, very nice, but sometimes this doesn't really work. And this doesn't work because we have sometimes we have complicated forces, and for those complicated forces, it's kind of difficult to write them down as nice formulas. It's difficult to write down a formula for the force or a formula for energy. Now I'm moving to slide number 3, and on slide number 3, I'm giving you 2 examples of this. One example is when you have, for example, when you have billiard balls. So let's say you're playing pool with your friends, and there are 2 balls. There is one billiard ball here, a second billiard ball here. And let's say this first ball, this is ball number 1, this is ball number 2. This first billiard ball is moving towards the second billiard ball. And then what will happen is that these 2 balls will collide. And then, then it kind of depends. They will both, in principle, they could both be moving with some velocity. So this is ball 1, this is ball 2. And now let's say we want to kind of figure out, let's say we know initial velocity of ball number 1, and we want to compute what happens after collision. So what are the velocities of ball number 1 and ball number 2 after collision? Now to do this, what you would have to do is you would have to write down some sort of formula expression for the forces. And so let's think how how this can be done. You have 2 balls. When they collide, what's happening exactly? What kind of forces are we dealing with? And if you think about it, these forces are kind of pretty complicated forces. Yeah. So what's happening here during collision is that these balls, when they collide, they will slightly deform. Yeah, they're not going to be spherical anymore. I will draw an exaggerated version of this, but you will have 2 balls that will be slightly squashed like this. And because they're squashed, there will be some elastic forces. These billiard balls, they would like to preserve their shape. And when they get squashed, they want to go back to their original shape. And because of this, there will be, some pretty complicated forces in here, and those forces will cause these balls to bounce off each other. But if you ask me, it's kind of easy to explain this in words, but if you ask me to write down formula for the force, that would be, pretty difficult to do, right? Because these forces, they change in time, and, there is no simple formula that describes them really. So the question is, what do we do? Do we completely give up on this, or is there a... And so it turns out there is a solution. Turns out there are some things that we can still do, even if we don't know exactly what's happening in between here. And that's kind of the subject of today's lecture. Today we will learn about how to deal with these kinds of situations. Okay, so now let's look at the second example that I give on my lecture slides. And the second example is when you have a bullet. You have this bullet, you're shooting this bullet, and you have a box over here. For simplicity, let's say there is no friction. Okay. So let's think about what happens when bullet hits the box. So this bullet will fly, it will collide with the box, it will get stuck in the box. And then, I mean, intuitively, it's clear that because of this, the box and the bullet that's stuck in the box, both of them will start moving, to the right. Now, let's say I know the velocity of my bullet, and I know the mass of my bullet, and I know the mass of my box. And what I want to do is I want to figure out how fast this box will be moving after this bullet gets stuck in it. So how do I do this? Again, to do this properly, I would have to write down the forces. So I would have to figure out what's the force of the bullet on the box as the bullet goes through the box. And this is, again, this is not easy to do. There are lots of complicated things happening in here. And it would be very difficult to write down a simple equation that would describe how the force changes in time. So this is another example where, writing down Newton's equations and solving your problem with Newton's equations would be complicated. So again, we need some sort of, technique, some sort of method to deal with these kinds of situations. Okay, so how do we do this? How do we deal with these kinds of situations? Basically, what we want to do is we want to see if, when we don't know the exact nature of forces, is there still something that we can say about interactions? I would like now to move to slide number 4. On slide number 4, I have this simple example of an astronaut floating in space. This astronaut is holding, let's say, a wrench. And let's say initially this astronaut and this wrench are stationary. So they're not, with respect to our reference frame, let's say they're not moving. Now, let's also say that at some point in time, this astronaut throws this wrench. Yeah, so he throws the wrench by applying some force to it. So this is a force. And after this astronaut throws the wrench will be moving towards the right. So this is the wrench flying to the right with some velocity, and the astronaut will be flying to the left, also with some velocity. Let's call this V sub W, let's call this V sub A. Now, I don't really know how much force the astronaut applied, and also this force was probably variable. It probably varied in time. But after this interaction happened, both of them are flying. There are no other objects in space, so they will continue flying with constant velocity. And I want to see if there is a way for me to say something about these velocities. Velocity of the astronaut and velocity of the wrench. So first of all, let's try to understand what's happening here. We have this astronaut that's applying a force over some time. But we know from Newton's third law that if you are applying a force, if the astronaut is applying a force on a wrench, then this wrench is also applying a force on the astronaut. And the force of the wrench on the astronaut is the same force in magnitude, but it has opposite direction. So this is the force of the astronaut, and we have an opposite force from wrench on the astronaut. So those forces are equal. Now, what do those forces do? Okay, so let's look at this situation from the point of view of the wrench. You have a wrench sitting here. This wrench experiences some force over some time. And we know from Newton's second law that the force is equal to mass times acceleration. So while this force is acting on the wrench is accelerating. We also know that acceleration is the derivative of velocity. Acceleration is telling us how fast the velocity is changing. So I can rewrite this equation as the force is equal to mass times the change in velocity. And now if I have this force applied over some time, then I know that the effect of this will be that my velocity will change. So the force applied over some time, summed up over a certain time interval, will be the integral of this. And the integral of derivative is the velocity itself, of course. So the effect of this force will be that my velocity will change. So, okay, so some force happened, and as a result, my velocity changed. Now let's do the same thing of this astronaut. I have this astronaut sitting here. It experiences a force from the wrench. I can basically write down exactly the same equation for the astronaut. I can say that this force is equal to the mass of the astronaut times its acceleration. And if this force is acting over some time, I can integrate the effect of this force, and I can say that as a result of this force, the velocity of the astronaut changes. Okay, so I have a very similar formula for the astronaut. I have some force acting on it, and I have some change in velocity. And now the key observation here is that the forces are actually equal and opposite in direction. So this will be the same as this, but with a minus sign. And so after I do this observation, I can write down the mass of the astronaut times change in its velocity is equal to the mass of the wrench times the change in wrench's velocity, but with a minus sign. So I will circle this and I will highlight this because this is kind of a very important result that we will be discussing for the rest of this lecture. Okay, let's pause for a second and let's think about what this result really means. So what's the meaning of this? Yeah. M times delta V of the astronaut with a negative sign is equal to M times delta V of the wrench. So first of all, let's think about delta V part. Yeah, change in velocity. My initial velocity was 0 for both the wrench and the astronaut. So your change in velocity is really your final velocity, right? Because in the beginning you had no velocity. So let me rewrite this as negative mass of the astronaut times astronaut's velocity is equal to mass of the wrench times the wrench's velocity. So these two things must be equal. The meaning of the negative sign is, I think, clear. The negative sign means that they are moving in the opposite directions. Now, what can we say about the velocities? If we rearrange this formula like so, then we will see that velocity of the astronaut is related to the velocity of the range by the ratio of their masses. So if astronaut is very heavy, then it will have a much lower velocity compared to the range. And the other way around. If the range is very heavy, then the astronaut will have a high velocity compared to the range. I think all of this kind of makes intuitive sense. Now, a very important point about this is that we didn't really have to specify anything about the forces. We didn't know what kind of forces there were, what was the formula, how big the forces were, for how long the forces acted. We had none of that information, but still we were able to deduce that the change in velocity is kind of inversely proportional to the mass. And that's why this result is very, very important. This result is pretty general, and it works for any interaction and any force as long as the third law of Newton holds. There was also nothing special really about the astronaut or the range. Whatever we did, we could have done for any two objects. So this formula is, again, very general. It applies to any two objects that interact with each other. Okay, so let me erase this astronaut. Let me look at the equation. And what I want to do now is I want to rewrite this equation so that it's kind of easier to use. I'm moving now to slide number 5 that says conservation of momentum. So what I will do is instead of A and W, I will just write 1 and 2 for object number 1 and object number 2. So what I can do with this equation is I can rearrange it. I can, put this piece on the other side, and if I do that, I will have the following. I will have 0 equal to m2 times delta v2 plus m1 times delta v1. Now let's do a bit more. Let's think about what this delta v2 and delta v1 mean. Those are the changes in velocity. So that's velocity final minus velocity initial. And for the object number 1, I also have its velocity final minus its velocity initial. And what I will now do is I will put everything that's initial on one side of the equation and everything that's final on the other side of the equation. So these two guys will move over here. And I will get m2 times v2 initial plus m1 times v1 initial is equal to m2 times v2 final plus m1 times v1 final. Now this equation looks pretty interesting. So if you look at this equation, you will see that there is something that we computed in the beginning at the initial stage. And then there is exactly the same thing that we computed after the interaction at the final stage. And this thing, m times v plus m times v, is has the same numeric value in the beginning and towards the end. Yeah. So this is kind of similar to what we had for the energy conservation, where we had something that we could compute in the beginning, and this thing kept its numeric value and had the same numeric value everywhere, towards the end of the interaction. So in this case, the thing that's conserved is m times v. What I will do is I will take this m times v, mass times velocity, And I will, since this is an important quantity, I will call it a name. I will call it momentum. And then if I give this m times v a name, momentum, and usually we will be denoting it by p, by a letter p, then I can write that the momentum of particle 1 plus the momentum of particle 2 in the beginning, initial, is equal to the momentum of particle 1 plus the momentum of particle 2 at the end, the final. And this means that the momentum is conserved. When you have interactions, things change, velocities change, objects may exchange energies, but whatever happens, the numerical value of total momentum always stays the same. Okay, so I will erase everything here, and I will just write our main result at the top. Our main result is that momentum is conserved. I will just write it in words. Momentum is conserved, and momentum is the sum over mass times velocity. So this is very nice because now we have a second conservation law. We had conservation of energy, now we have conservation of momentum. There is one more thing that we know is conserved when things interact. So let's look at this conservation of momentum. Let's compare it with the conservation of energy. Just to remind you, the conservation of energy told us that mass times velocity squared divided by 2 plus a bunch of potential energies was conserved. And the conservation of momentum tells us that mass times velocity is conserved. So how are these conservation laws related? What's similar between them? What's different? So one important difference is that unlike energy, which is just a number, so this is just a number, momentum is actually a vector. And momentum being a vector means that it has direction and it has magnitude. Yeah. So, for example, if you're moving in this direction with some velocity of 5 meters per second, and then after some time, if you turn and if you move this way with 5 meters per second, your energy didn't actually change. You have exactly the same energy, kinetic energy, but your momentum did change. Momentum is a vector, so 5 meters per second to the right is not the same as 5 meters per second down. And the second difference between the conservation of momentum and the conservation of energy is that even though they, in some circumstances, they are both conserved, those circumstances are kind of different. So you may have cases where, for example, momentum is conserved while energy isn't. Now, when we derived conservation of momentum, we did this for just 2 interacting particles, but the conservation of momentum is true for basically any number of particles, as long as there is no external force. So if you have, 5 particles, 1, 2, 3, 4, 5, and if they all interact somehow between each other, let's say there are forces. This could be a force of gravity or some other kind of force. Then those 5 particles will move around. After 5 seconds, they may be here. The distribution may look like this. But the conservation of momentum is still something that holds. So if you take momentum of all 5 particles, m1 v1 plus m2 v2, and so on. And if you compute it at the beginning, and then after some time passes, if you compute momentum towards the end, m1 v1 plus m2 v2, you will find that the total momentum of all 5 particles is conserved as long as there are no external forces. Okay, so this was all, very nice, but also very theoretical. So what I will do next is I will look at four problems, specific problems with specific objects moving. I will try to solve them using conservation of momentum, and hopefully it will become clearer why the conservation of momentum is such a big deal.